So welcome to the Markovnikov learning module, okay? And the reason that I say it that way is because Markovnikov is going to be rooted in organic chemistry quite a bit. So part of these videos are going to introduce you to the organic chemistry topics, and then the other part of the video will concern the actual laboratory when you do it. Here's the thing though, before you watch any further. If you just so happen to pick this lab as one of your first, then my advice to you is to shut me off and then go pick another lab and do those first. And then come back to this lab about midway through. So 3 to 4 weeks into the process, then revisit the Markovnikov. And I think that you will have enough background and foundation under your belt in order to accomplish this lab and get very good numbers and good products at the very end. The reason this is a very complicated lab, it's going to require 2 to 3 days of your time at least just for the reaction portion, and then you're going to have to follow up with that with the lab write-up and the detailed information that goes into your lab notebook. So go do other labs before you tackle the Markovnikov. Now, I want to spell Markovnikov. So Markovnikov, Markovnikov. And this is Markovnikov's rule. So the reason that we have to talk about this is because in organic chemistry, like most chemistries or lab-based science courses, we're going to have to do something. And that something typically involves taking a compound and reacting it with another compound and creating something new in the very end, right? That's kind of our job. We take these two things, we do something to them, and we get a product. And that product is something completely different than what we started with. So the question here that we have, that we always have working in a laboratory very often, is why? Why did it happen? Why did those things react the way that they did? Why did that product form the way that it did? And then how? How did those steps occur? And that's really the root of organic chemistry. We have to explain why these things are coming together to give us a product, and then we have to explain ourselves. We're going to have to give you details about how this product came into an existence, right? So that's what Markovnikov's rule is going to play off of. So this rule is quite old. And when I say that, at least it's a little older than I am. This goes back to 1870. So in 1870, Markovnikov was in a laboratory and was basically doing experiments, and he was getting these products from the reactions, and he noticed a trend. And that trend he wrote and reported about, and those manuscripts and those publications became to get noticed, and people were like, oh, that makes sense, and this works the majority of the time. So I think that we can call this a rule, and I think that we can go by what Markovnikov is reporting, and we can kind of say that this takes place for the most part across the board, and it makes sense. So we need to talk about this rule, but before we do that, we're going to have to give you some basics of organic chemistry. All right, so first off, there is a set of molecules called an alkane, and that has an ANE ending. And alkanes are molecules with single bonds. So that means if I've got a carbon bonded to a carbon, bonded to a carbon, bonded to a carbon, all of those are single. Therefore, that is classified as an alkane, a carbon-to-carbon single bond. All right, well, the next set is something called an alkene with an ENE ending. And those have at least one double bond. So here's a molecule that I just drew from above, and then if I put that double bond, just one of them, in the molecule somewhere, as long as one is present, that is going to be called an alkene, right? And then we have the third group, and that third group is called an alkyne with a YNE ending. And this involves a triple bond, and it just needs one. So if I start with my very first molecule that I drew up above, if I do a triple bond in the molecule somewhere, doesn't really matter, between two carbons, and there just needs to be one, that is called an alkyne. So alkane, alkene, and alkyne. Markovnikov's rule is very important when it concerns the alkene and the alkyne chemistry. And you're going to see why in just a few minutes. All right? Now, in organic chemistry, there are also molecules called symmetrical and unsymmetrical. So, let me give you an example. If I do the molecule up above, and I do 4 carbons, and I put a double bond directly in the middle, if I look at that double bond and I just kind of draw a dotted line, and I look at the pieces to the left and I look at the pieces to the right, these are the same. This is what we call a symmetrical molecule. Markovnikov's rule doesn't really do anything to symmetrical molecules, right? We don't really have to use the rule in order to determine the proper product that gets formed from the reactions. They're symmetrical. So no matter which way I look at it, I'm going to end up getting the proper product because the molecule is the same on the left as it is on the right. So who cares? The issue that we have, that organic chemists have, back in the day and even today, working in a laboratory with these molecules, very rarely will they be symmetrical. Instead, we might have a 4-carbon chain, for instance, and instead of the double bond being smack dab in the middle, it might be on the end. So if I look at this double bond and I kind of draw a dotted line, the area to the left and the area to the right are different. I've got 1 carbon to the left and 3 carbons to the right. So this is called an unsymmetrical molecule, right? We're not saying that you have to be a rocket scientist to understand how this works. So hopefully that kind of makes sense. It's not symmetrical. It's not the same on both sides of that double bond that I want to focus on. Okay, well, Markovnikov's rule not only does alkenes and alkynes, but Markovnikov's rule also deals with unsymmetrical molecules. Unsymmetrical alkenes and unsymmetrical alkynes. That is what we're after. That's what we're discussing. If you have alkanes, who cares? Markovnikov's rule is not going to play into the picture. We'll talk about why in just a few minutes. If you have a symmetrical molecule, Markovnikov's rule, it's not going to play any matter. It's not going to be any different. Who cares if you know what Markovnikov's rule or not if you look at those 2 classifications of compounds? Doesn't matter. It's only with unsymmetrical alkenes and unsymmetrical alkynes. All right. So what does this lead up to? Well, let's say that I have a molecule. We're going to keep it simple. And this molecule just involves 3 carbons, and let's say that there's a double bond here on the end. That is a unsymmetrical alkene. So Markovnikov's rule should give me some insight about what's to happen when we react this molecule with something else. So let's say that I react this with hydrobromic acid, HBr. Well, I know that most of you have not had organic chemistry yet. So I'm going to kind of explain this reaction in a very basic way. What I want you to keep in mind is that HBr is made up of 2 pieces, an H and a Br, right? Whenever we have alkenes, the double bond is going to be reactive. That means that that double bond can be manipulated into doing something that we want to do. And what we want to do with that double bond is really what we're adding to that double bond. And in this case, we're adding HBr. There's hundreds and hundreds of choices that I could do with this alkene. HBr is just one of them. All right, so this is what happens. When I have a double bond, the double bond can do what we call break. Now, I don't really like to use the word break. And the reason is because it gives people the weird idea that these double bonds or triple bonds or bonds in general are sticks, and these sticks can snap. And if you have a chemistry teacher to tell you that, they are lying to you and they don't know what they're talking about. It's not a stick. Give me a break. These sticks are just for us to draw on a sheet of paper that helps us understand maybe the structure a little bit better. There's no sticks there. All it is are electrons. These electrons are hanging out with each other. And the electrons are kind of like glue that keeps those two carbons together. And the more sticks that are drawn, the more electrons that are present, and those electrons help keep the carbons together. They pull them in a little bit closer. It's the glue that holds them together. Okay, well, because there's two lines that are drawn, there's two sets of electrons, and these electrons can be separated. Well, that is what we call break. The bond will be broken. So what happens in these reactions is that a double bond can break into a single bond. And when that double bond breaks, a site of attachment opens up on each carbon, right? It opens up for a new relationship. Carbon can have 4 bonds in total. Well, the one that's not drawn there is to hydrogens. But if that double bond is broken, all of a sudden, carbon's freed up a little bit, right? He's not taken in a relationship anymore. So that part of the carbon can go out and find something else to bond to and create a structure with. Well, if I'm adding HBr to this molecule, the carbon has a choice. It could maybe get an H or it could get a Br. The issue here is, which does it get? There's 2 carbons at play, not just one. And there's 2 choices that I'm adding, an H and a Br. So where do they end up going? That is what the purpose of Markovnikov's rule is. So for instance, in one example, a bromine could go here and a hydrogen could go there. And in another example, if the double bond breaks, 2 sites of attachment open up, well, maybe the Br could go here on the end and the H could go in the middle. Right? So I've got 2 choices. And the question is, well, which one of these actually go forward? Which one of these is actually the product? Well, the answer is both. You do get both of them. There's no control over it. This is just statistics, really. But one is preferred over the other. Okay? So what we do is that we call one the major product and we call one the minor product. So the minor one is the one that doesn't show up as much. The major one is the one that shows up almost every single time. So Markovnikov's rule will give you an idea of which one is the major and which one is the minor. So keep in mind that both choices happen. Both will go on in your flask. When you do these reactions, all of the choices will be swimming around in that bowling flask. This is one of the reasons that a very high percent yield is never going to be achieved with organic. Typically, on average, we're going to say give or take greater than 60% is very good when it concerns organic reactions. And the reason is because 40% of the product could be not your product. This could be the minor products that we do not want. These are the minor products that do not get pulled out of the major products when they form. So in a way, we like to call the minor products a contaminant, even though it's not really a contaminant, right? This naturally forms. There's no control over it. It's going to happen. Go cry boo-hoo. But because of that, we understand that organic reactions have a very low percent yield. And on average, we're looking at 50 to 60% for the most part. Okay? So in the next video, we're going to pick up with this idea of Markovnikov. And maybe we're going to explain it in a little bit more detail. I'll give you some more examples. And we'll talk about how this is going to relate to your lab that you're going to be doing after you finish watching my videos.